Hello students, this is Dr. Diaz and I'm here to talk a little bit about the nucleophiles. In classwork 12, some students had some questions and this was one of the questions, how to choose a good nucleophile. First thing that you need to take in consideration is the charge of the nucleophile, electronegativity, steric hindrances. Remember that I used the TERC butoxide as an example in class that I said it's a strong nucleophile but cannot be used in SNE2 because the steric hindrance, but can be used in elimination. And also the solvent use will can decrease the nucleophilicity. Remember that I said that if you use a product solvent with a strong nucleophile, this product solvent will reduce the nucleophilicity of the nucleophile. Okay, so this is the you can look at those factors to see if they're good nucleophile or not. Okay, so a nucleophile, let me just use another pen over here. So nucleophile, it's what do we call Leo's base, right? Leo's base. So that means when it donates a pair of electrons to an atom other than a proton, for your purpose, usually carbon atoms here. So you're gonna always use a carbon atom. What is nucleophilicity here? It's let me write the nucleophilicity is everything to do or measure. This is measured by reaction rate. So like here, if you have a steric hindrance like the teric butoxide, will reduce decrease the velocity of the reaction up to the point that you can say like that is not reaction. Okay, most of the reactions with the nucleophiles are unreversible or irreversible. Okay, so negative charge is a very good factor that you need to look at. For example, if I look for hydroxyl, okay, this is a very good nucleophile and much better than water. Because remember, charge turn the group or atom unstable. They need to be free of those charge. So when you have a charge, you have normally a good electrophile. So electronegativity. Let me thinking about how to explain this. So loosely held electrons are donated more readily. Okay, so nucleophilicity increase as electronegativity decrease. So nucleophilicity increase as the let me go back this, as the electronegativity decrease. So let's give you an example here. H2S, we have sulfur over here, and this will be bigger than phosphor. Okay, this is a good example. Another thing is the solvent that you need to look at. Remember that I said some solvents can decrease the nucleophilicity over here. Let me use another color pen. So solvent. So nucleophilicity or solvent will decrease. For example, if you use product, polar product solvent, this polar product solvent can decrease the nucleophilicity. So we need to use an SNE2, for example, to not decrease the nucleophilicity in SNE2. We need polar A product solvents. Okay, A good example, DMF, DMSO, or acetone. Okay, these are good solvents for this. So the solvents, because the solvent cannot make hydrogen bonds, this will make hydrogen bonds with the nucleophile. So, and that will decrease nucleophilicity over here, okay? The other thing that I said was the steric hindrance. So steric hindrance, use another color of pen. Steric hindrance. So steric hindrance is when you have a book base or book nucleophile that we decrease the capacity of the nucleophile to attack the substrate. So, and the nucleophilicity here will decrease. Nucleophilicity will decrease with the increase of the steric hindrance. Okay, since increased bulkiness make it more difficult to approach orbitals on carbon atoms. Remember this, right? So remember the example that I gave in class. So we have this, for example, this nucleophile, which is good nucleophile, and we can compare with this over here, for example, this over here. This is very already book base, which is still, it's very smaller compared with this one, the first one, but this is still bigger if you have a tertiary carbon over here because it's more bucket. This is the example that I gave you in the class, remember? Tertiary oxide. So this is the worst nucleophile here, okay? Because it's most book, right? And this is the best one, since this is the least. Okay, that's it. That's all.